Welcome everybody. Now, this is a paper I'm truly excited about, okay? So the previous paper is something I do not think is nice. This one here is really something I'd like you to remember when this conference is over. If you look down here, you can see that I also put this excitement on the slide. So, I mean, I really think this is sort of like some of the best work I ever did. So let's see if I can convince you of that. Okay, this is just saying we're using multiple valued state variables. This is saying I'm going to be using a logistic style problem to illustrate. Now, here's already sort of the idea in a nutshell. When you look at this example here, you all see, or if you're familiar with causal graphs, you know that this is what the causal graph looks like. Okay, I mean, it's basically saying each package depends on the truck. Yes, because the truck provides the preconditions the package needs to be loaded and unloaded. So, okay, now if you look at this structure here, and for the moment we abstract from what we're actually doing and we pretend that this is a graphical model, okay, say a Bayesian network. Now, if this was a Bayesian network, obviously we would have a conditional independence here, right? Sort of the packages are conditionally independent given the truck. Now, this being a graphical model, what I would like to do is instantiate the variable in the middle so that the rest falls apart and I can solve it easily. Now, back to reality, it's not actually a graphical model. It's a structural property of a high-level description of a large state transition system. So what does it mean to instantiate the variable in the middle? Well, here's an idea. We can fix a sequence of moves for the action, for the variables in the middle of this. Okay. So you take out the thing in the middle by fixing a sequence of moves for that. Now, if you do that, if you fix a sequence of moves for the truck, what each package can do is, well, do whatever it can do given those moves. But this is independent for each package relative to the other packages. So by fixing the truck moves, I can break the dependencies between the packages, which only depend with each other via the truck. Okay. Now, this was like a very brief glimpse of the idea. Of course, I'm going to spell it out in more detail later on. First of all, like, where is this like in our topology of planning methods? It's one way of it's in the family of factor planning methods. When I say factoring, I mean a partitioning of the state variables, like truck, package, okay? Each of those would be a factor. You all know there's a long history of factor planning. I'm not going to really go into this. The one thing they all share is that they cater for arbitrary cross-factor interactions. So nobody ever restricts the topology of their agents. They might be trying to get a simple topology, but in principle, they can handle arbitrary topologies. Now, this here is different in the sense that I actually force the factoring to induce a fork profile. Okay, so I will present a factoring strategy later which does that. Of course, not all planning tasks have an inherent fork structure, and in those the method will just abstain and say, sorry, I can't do anything about that. But a priori, we only deal with things that take the form of a fork. Now, why am I so enthusiastic about this? You might think, well, one thing is it opens a whole universe of future work, like really like for sub-communities, plural. I'll explain it later. The other reason I'm very enthusiastic about this is, of course, the empirical results, right? So, I mean, you know, if it worked badly, then probably I wouldn't spend the next 10 years researching it. Now, it works quite well. If you look at this table, what you see is state space size. Okay. Left column, standard state space. Next column, under partial order reduction, state of the art by Malte and Martin. Next column is a version of a technique that allows to extract optimal plans. Next column is a version of the technique that allows for satisfying planning, like plan existence basically, and the proof unsolvability. I think the numbers pretty much speak for themselves, right? Not that much to add. Have you noticed TPP already? Unsolvable no mystery also is fun. Now, there are some caveats here, and I'll get to those later. For the moment, let me just explain what this thing does. Okay, so how do we achieve this reduction? Here's like sort of my example back again, and those red things here I've basically already said. So what I'm going to be doing is briefly lead you through this example and show you what the method does. It's going to take the form of a table. Okay, so our table starts with two states, and I'm also showing this. I'm showing you basically the search for along one prefix of truck moves. So the prefix is also shown by the illustration up here. Anyway, down here, what I'm saying is, okay, initially I'm in Vancouver, and then I'm moving to Edmonton. Now, what I'll be doing alongside this is for each package separately, just, you know, keep track of what the package can do given this truck move prefix. So in the first step, the package number 1, which is in Vancouver, can be loaded, or it can load itself. You can also think of it as an agent if you want. So the package can be loaded into the truck, and therefore we get this new value of the variable. So this here is a set of values of the variable that we can reach. Now, why is it a set of values? It's because I'm not actually committing to this. Now, usually when you search, you either commit to not loading the package or commit to loading the package. I do none of that here. I'm just saying if I wanted to, I could load the package now. So I'm just collecting sort of possible values for each of the leaves, and which ones I'll actually select, I will just decide later on when I've reached the goal, and then I just extract the path achieving the goal for each package separately. Again, it's a bit of a preview, but this is what's happening here. Then at the next stage, I can drop the package or unload it at Edmonton, right? So now I have 3 possible values where I could be, and all of those are fine. I mean, I'm just saying, given this sequence of truck moves you committed to, any of those you could actually achieve if you wanted to. Same for the other packages, okay? Now, another thing at this point, so now we have completed one search step. So what I just did is one state expansion. I've expanded the state. Okay, so I've applied an action in the center. I've moved the truck, and then I'm not done with that. So usually we're done. We've applied the action. We have the outcome state. We're done. Now what I also need to do is say, okay, given this move I just committed to for the center, what could the packages do? And this is what I do here. I write down this column. So each state in the search space is like a center state combined with possible locations for the packages. So like one column in this table is one search state in our search space. Anyway, let me continue down the search path. I move on to Toronto. What can the packages do? Well, this guy here can now also be downloaded at Toronto. Unloaded in Toronto. The other guys can also go to Toronto. The guy who was initially in Toronto can now go into the truck. I continue this path again. I go back and note that this actually goes back to the same center state. So as far as the truck is concerned, there's no point in going back to Edmonton. However, we still have to explore this search state because the behavior of the leaves changes. So it's a search over truck, over center paths, rather than center states. Anyway, for those 3 packages, it doesn't matter. For the last packages matters because it was only loaded here, and now it can unload itself in Edmonton. So this is sort of like an example glimpse of what's going on. I'm going to spell this out in a little more detail on the next 2 slides. So we call it a decoupled search. We search only over the center. And in each search set, we maintain what the leaves could do. I might have said or written the word compliant leaf path already. And this is sort of like a central notion. I'm going to explain it now. A center path is just what the truck can do. And because the truck doesn't have any preconditions on anything else, and that's by construction, it's in the center. It doesn't rely on any other variable. I can just move it wherever I want. Not so for the leaves, they depend on the truck. But a priori, a leaf path is just something that's applicable in a projection on the leaf. And now given a center path, a compliant leaf path is one whose center preconditions, whose preconditions on the center can be satisfied. So given this center path here, this moves of the truck, this leaf path for the package 4 is compliant because I can insert it at those points alongside the truck moves. So the global plan would look like this. We just insert the actions at those points, and now here's what the fork structure gives us. It gives us the property that every global plan decomposes into a center path and independent paths for the leaves. So like every global plan can be decomposed into whatever the center does, and then a leaf path that complies with this and reaches the leaf goal for every leaf separately. Okay. Now, here's our actual search space. It's a transition system. It's just not the usual transition system. Our states are combinations of center states and what we call a pricing function. Okay. The pricing function maps leaf state to numbers, and the intended meaning of those numbers is this is the price you would have to pay if you wanted to get this leaf into this leaf state at this point in time. Okay. Now, these are just the states. Here's the actual transition system. The branching is only over the center actions, so like you can understand this as what we gain from this is we don't have to branch over the leaf actions at all. We only branch over the center. The goal states are just ones where every leaf has a finite price goal leaf state. Okay, so now for every leaf, there is something you have already reached. I mean, infinite price just means you cannot reach this leaf state at all yet. You're in a goal state if for every leaf you can reach the goal. The initial state doesn't just list what we already have, it also lists what we can do given the center initial state. Okay. So for the center, it's just as usual. For each leaf, we take whatever we can reach on a path of actions whose center preconditions are satisfied in this particular center state. Okay. And then, of course, our pricing function takes the cheapest path. So this is like finding the cheapest path in a graph, and the graph will be small because we ensure that the leaf state spaces are small. Accordingly, when we make a transition, we first transition the center state as usual. So we go from the center state S to the center state T, basically. How do we get the new pricing function? Well, we take the previous pricing function here, and then we just attach cheapest paths to get the prices in T. And those cheapest paths must use the center precondition from T. Okay, that's what I'm saying here. I mean, basically, you just say, okay, do whatever you had before, and then try if you can get something cheaper than before by using the new center preconditions that T provides to you. Central correctness lemma is that those pricing functions actually correspond to the prices, to the cost of the cheapest compliant leaf paths at any point in time. So by this incremental construction, we actually get the cheapest possible compliant leaf paths. It's quite simple. What do I do when I've reached the decoupled go state? Well, I extract the solution by just committing to the center path, and for each leaf, retracing a cheapest compliant path from the information I maintained in the search state. And then necessarily, this will give me a global plan. And necessarily, if the overall cost of this is minimal, it's also minimal in the original problem. So in other words, this is a method for optimal planning. Now, I can also use it for satisfying planning and whatnot, but this is just saying it's possible to use it as an admissible search decomposition technique. Okay, we don't have to, but we can. Okay, so if I find the optimal solution in this strange decoupled search space, I get an optimal plan. How do I actually search that space? The short message is I can adapt heuristic search methods relatively easily. The next 3 slides gives a slightly longer message. Heuristic functions are still what you think as usual. However, we have 2 different kinds of heuristics, and this is important. They actually can play a different role in search algorithms. A center heuristic estimates only the remaining cost for the center. This means how much work do I still have to do so that every leaf can do whatever it wants to do, can reach their goal, but I don't care how much of the price the leaves are going to have to pay. I'm willing to live with the leaves paying more than it would need to do. I just care about my own cost, whereas the fork heuristic estimates the remaining cost of the whole thing. How can we get those heuristics? I'm going to skip those details over. We just compile into classical planning. The nice thing about those compilations for both kinds of heuristics is that if the original heuristic function was admissible, it is admissible now. If it was initially perfect, it is perfect now. So a very basic way of preserving information in heuristic. How do I search? There's one subtlety. In a decoupled go state, you have only now paid the price for the center path, not for the leaves. You still have to buy the leaf goals. Okay. And the heuristic will actually see that if we say, no, the cost is not 0. And actually, the best path might traverse a goal state and then find a better goal state later on. So that's not something we usually see or like to see. There's a very simple compilation that gets rid of this. Okay. You just encode the buying of the leaf goals into a separate transition in your search space. You can apply any search algorithm you want. It's going to work. When I take this is like a search algorithm X. When I say FDX, I mean Fork-Decoupled X. And it's going to be optimal if the original one was optimal. Here's a specialized search algorithm. Please don't read the code. Just look at the blue stuff. It's using 2 heuristics, okay, both kinds of heuristics. It runs A star in the center, which means it prefers shorter paths for the center. Because of that, to find a global optimum, you have to continue until the open list is empty. However, I can use the fork heuristic to prune that search space relative to the best upper bound I've found already. And the only reason why this is interesting is that there's an early termination. If like the leaves already go the best possible paths they have in their projection, like they couldn't possibly get better, then we can stop because we found the optimal plan. Think packages. What kind of package do? I mean, go into the truck, go to the goal. Those are not complicated paths. So I mean, this is a typical problem where this kind of condition applies. Back to the experiments. I first have to explain the factoring method. It's very simple. You take the graph of strongly connected components of the causal graph. You make a horizontal line in the middle. Like here, this would be truck and fuel, and then each package is a leaf. Or here in the center, you could have machines, and around this, you could have objects being processed by the machines. Essentially, any situation where you have set of agents or whatever that share common resources, you put the resources into the center, you get this kind of topology. Now, if the causal graph is only a single strongly connected component, we can't do this, right? And in this case, we abstain. In fact, we even abstain if we only find a factoring that has a single leaf. Now, we did find single leaf factorings that were useful, but not so many, and we didn't really know how to handle this, and we just kept it simple. So we only actually apply this technique if there's more than one leaf in whatever factoring we find. Good. I showed you previously that we reduce state space size. Does it carry over when you use an actual heuristic? The answer is yes. Just look at those colored things here. This is like the reduction factor relative to A star with LM cut on the standard search space. over all evaluations, like calls to the heuristic function across the entire domain. You see that POR is very complementary to our method. The only domain where they overlap is woodworking, and their POR actually works better than we do. But there's many domains where we win here. Now I'm only going to show you results for optimal planning because that's what in the paper. In the meantime, we have results for satisfying planning for proving unsolvability as well. But those are for optimal planning. What are the caveats? So, I mean, is it really that wonderful? Well, there's two things. One is decoupled states are bigger than standard states, right? The good news here is that the leaves are usually small. I mean, we could even force them to be small. In most of the factorings, we find the way we do anyhow, they are small. So it's an overhead. It's not such a big overhead. Second thing is, well, the domains not in the table are not there because we don't do anything about them. Okay, we abstain on all of them. Now that, of course, limits the scope of the technique, but you know the way I have to view it is actually this is that technique that tells you where it doesn't work. All of our search pruning techniques only work in some domains. This is just how life is. This one actually tells you where it works. You run the factoring strategy. If it says if it can't handle this, then it abstains, and it abstains in 0.0 seconds according to FD. Okay, pretty much always. So you don't waste any time. You can just call another planner. The number of domains where improved coverage. So this is coverage. Really don't look at all the numbers. Just the colored stuff is where we are good. In the bottom line, we are very good. The number of domains where improved coverage is pretty much the same as the number of domains where partial auto reduction improves coverage. And partial auto reduction, I might mention, has been invented 20 years ago. Well, this is something that Daniel implemented in his master thesis. Okay. So there's lots of more things to do. In 3 domains, which is kind of fun, even if you use LM-cut in the standard search and H-max or blind heuristic in our search, we still beat it. Okay, so like in domains where it works like hell. It just, you know, gets rid of the whole problem. Okay, I have very little time left, but let me try to get through this. So I said subcommunities plural. What did I mean with this? Well, first of all, actually, this is not future work because, well, it's going to be presented next week at SOX. We've already generalized it to stars rather than forks. You can have bidirectional dependencies between the leaves and the center. You can even have like side effects between the center and the leaf. We can star decouple any planning task just by cutting it in 2 pieces. One is the center, one is the leaf. That's a single leaf factoring. It might be useful. We still have to explore it. Really, my main point here is, okay, we can count the IPC benchmarks, but is it really meaningful? I mean, you know, somebody creates a benchmark. If my technique works, I'm lucky. If not, I'm not. For this particular technique, at least, it's much more meaningful to look at applications that naturally have a star topology. One example being cooperative agents with shared resources. Okay. Another example being model checking. You might have heard of client-server architectures at some point, right? So what I'm actually planning to do is implement this in Spin and then apply it to whatever problems they are looking at currently, like actually weak memory models in multi-core architectures are one very interesting example. We can do a probabilistic adversarial, whatever you want. I actually start to see star topologies everywhere. Look at this game board. It has a star topology, right? Doesn't it? Actually, it doesn't even have to be that obvious. You can take any game board, draw a borderline across this, call the borderline the center, and everything around it disconnected by the borderline becomes a leaf. So that's also something I'm planning to do. Finally, this is for forks and stars. Okay. Is this the only thing we could use? Well, no. We can just design arbitrary structures and design combinatorial search algorithms suitable for those structures. Now, I can't tell you what those structures are. One instruction for finding them I can give you is just, you know, go through all the causal graph literature, and rather than consider intractability, consider specialized combinatorial search algorithms. And the long-term vision here is, you know, given any input planning task, just select whatever structure and factoring seems to fit it best, and use the specialized combinatorial search algorithm for that. If you will, this is a way of using domain-dependent planning without having to focus on a particular application. Instead, we just focus on a particular structure. So this is actually a path that I think is very fruitful, very useful to look into. One nice thing is that every time you exchange the search space for something else, you also have to reinvent all the search enhancement techniques, so we can write lots and lots and lots of papers about that. I hope I'm not going to have to write them all on my own. That's it. Thanks.